This first example is a very straightforward look at the ratio idea between the turns or the windings versus the voltage. The key idea here is that the output should be related to the input in the same way for voltage or for turns. You can also think of this as the secondary versus the primary, however works best for you. In either case, let's take a look at the voltage. So the primary voltage is 300 volts. So I'll put that on the bottom of my fraction. That's the input. And the secondary voltage is 180. That's what we're bringing out. So this is a step down transformer. And then according to the turns idea, the primary winding, okay, that's what we call the coils, has 1150 turns. So that's going to go on the bottom. And we are going to calculate the number of turns needed in the secondary. So this is our N. So we could just cross multiply here, and when we work out the algebra, we end up with N equals 690 turns. Fewer turns on the secondary than on the primary. Okay, this example has, again, kind of a straightforward output versus input idea. So output versus in, or if you prefer, secondary versus primary. Just want to make sure you keep the top and bottom corresponding to each other. You could do primary versus secondary as well, as long as you're consistent on both sides. So here we want to calculate the output voltage. Okay, so we don't know the output or the secondary voltage. The primary voltage is 230, so that'll go on the bottom. And then in terms of the turns or the windings, the secondary coil has 290, and the primary coil has 1120. So again, we can cross multiply, and we find that our voltage, which should be smaller, okay, it's a step down transformer, the voltage ends up being 59.6 volts. And we'll use that in the second part. Second part of the question talks about the current in the coil. So the current, you can do sort of an inverse ratio, but I tend to get a little bit more confused with that. I like to just think about power ideas. So the power has to be the same in the secondary and in the primary, and power is voltage times current. So if I take the voltage in the primary, so that's up here, that was our 230, and I multiply it times the current in the primary, okay, that's what we were given, that should equal the voltage for the secondary. That's what we found in the first part of this problem, so 59.6 volts, times the current in the secondary, that's our question mark, or unknown. And then we multiply and then divide by 59.6, and we find that that current in the secondary is higher, 9.6 amps. That's because this is a step down, which is the voltage, which means the current must be stepped up. But it's called a step down. It refers to the voltage. All right, this final example deals with a more realistic situation where power is not actually conserved. So we have been looking at really an ideal situation to say that the power in is equal to the power out. Generally, there will be losses due to heat and so forth. So this soldering gun, which is used for electronics and so forth, is only 80% efficient. So what we need to do here is we need to find out how much power we're starting with, the power that's input or the power of the primary, and then multiply that by 0.8 so that we figure out how much remains, and then use that to determine the current in the secondary. So the power that's coming in, again, voltage times current, the voltage. Okay, now there is a voltage given, 24 volts, but that's the expected voltage at the output. Okay, so that's not what I'm using. But this is a tool that's going to be used in our home. It's American made. That's our hint to tell us that the voltage is 120, like it is in our household sockets here. And the current through the primary is 0.4 amps. Okay, so we can determine that the power is 48 watts for the input. Again, with an ideal transformer, which is what the first two problems dealt with, the power out would also be 48 watts, but we are losing power. This tool is only 80% efficient. So we'll take 48 watts and we'll multiply it by 0.8 to represent that inefficiency, and that brings us down to 38.4 watts. And that now is our output power. So power is voltage times current, so 38.4 watts should equal our output voltage, which we know is 24, times our output current, or our secondary current. That's what we're trying to find. So 38.4 divided by 24 volts, our current is 1.6 amps.